Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were talking about the interaction between magnets, right? So if we bring two magnets together, how does a magnetic field change? The reason why we were talking about this is that we want to now bring this discussion into the context of electrical machines. So for example, we want to bring this topic, or rather this concept, and describe how the interaction between the stator magnetic field and the rotor magnetic field results in a force that is being produced, and that force in turn results in a torque which causes the machine to rotate. So this is where we are going in this lecture, going to start talking about how magnetic fields interact, but more in the electrical sense. So for example, if there was a magnetic field which was passing through, or rather interacting with, a current carrying conductor, what kind of a magnetic force will be produced on that conductor? And for this reason, we will talk about how the magnetic fields interact between the magnetic field produced by the current carrying conductor and the external magnetic field. So this is, before I start this lecture, as always, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So this is the home page of the project, and these 4 buttons will take you to most of the contents which are available on the website, and besides, of course, you can always scroll through the rest of them. So if you click on this button, Learn, it will take you to the list of courses which I have currently. So for now, I have 5 courses. The very first course I have is called Simulating Power Electronic Circuits Using Python. And in this, I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python and packages such as the SciPy package, and within that, the Signal package, to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers specifically for power engineering applications, with the example of a single phase inverter connected to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is a motivational course, free motivational course, targeted towards junior undergraduate students or even high school students who have not yet chosen their domain of specialization, to talk about some of the opportunities and challenges available in power electronics. So all these courses are hosted on 2 platforms, which is Decibel Labs and Udemy. You can click on any of these buttons to take you to the link for the course. So the link for this page is provided in the description of this video. If you're interested, please do check it out. So with this, I will return back to my lecture. So as I already said, this is what we are trying to do. We are trying to figure out how torque is produced, and for that we need to figure out how force is produced. So to figure out how force is produced, we need to now create a similar flux pattern for when a magnetic field interacts with a current carrying conductor. So for example, we have already drawn a few flux diagrams such as these. So for example, the idea behind these is to show the interaction between the stator flux and the rotor. So for example, in this case, the current is flowing in the stator windings. It is producing a flux. This flux is linking with the rotor as well as the stator. So there is a self-inductance and a mutual inductance. In this case, the current is flowing in the rotor and it is producing a magnetic field. And this magnetic field is linking with the rotor itself and also with the stator. So therefore, there is a self-inductance, or a rotor self-inductance, and there is also mutual inductance. Now the question is, using similar diagrams, how will we determine the force? So before we reach this level, we need to first talk about what happens in the case of just a magnetic field passing through a current carrying conductor. So let me just first draw a magnetic field. Let me just draw some straight lines. So these now this is, let's say, one magnetic field. I'm going to just draw an arrow to indicate that this is the direction of the magnetic field. And let me just select all of it. Let me just group it. So this is one magnetic field. Okay, you can see that this is an arrow, doesn't really look like much, but anyway. So if I just copy it and put it together, so this such a magnetic field could be said to be produced if, for example, we have a north pole of a magnet here and we have a south pole of a magnet here, right? So it doesn't matter how it's produced. Let's just, for example, let me draw a fictitious one. This is, let's say, a fictitious north pole and a fictitious south pole. For now, don't worry about where it comes from. Just put N and put S, right? And just because it's a north pole and a south pole, the magnetic lines of force will leave this north pole and will enter the south pole, right? Now, of course, there will be some few magnetic lines of force which will be fringing. We can ignore them. Let's just assume it to be a uniform magnetic field. So all these magnetic lines of force are parallel, and we can neglect all those magnetic fields which are actually fringing, which are curving, right? And which are not linear, where there could be some amount of fringing effect. We don't deal with those. Those are fairly complex. Now, at the same time, we've also talked about another case. That is, if, for example, we have a current carrying conductor. Let me just draw a current carrying conductor, which is like a really thin rectangle. And let us suppose this was carrying a current in the upward direction. So let me just draw a straight line and let me draw some arrows here. So this arrow indicates the direction of current flowing in this conductor. Now, if I were to say that this current carrying conductor this conductor were carrying such a current, then in that case, we've already known that the magnetic field produced by this consists of concentric circles with this conductor as a center, right? So we can say, so let me draw an ellipse. So if this current carrying conductor were to be in this vertical direction, then these magnetic lines of force will be in a horizontal plane perpendicular to this conductor. Now that we have drawn this, we now can say, use the right hand thumb rule to determine the direction in which these magnetic lines of force are flowing. So for example, if we grab this conductor with our right hand, with the thumb pointing in the direction of the current, then the direction in which the remaining 4 fingers encircle the conductor will be the direction of the magnetic field. So if you were to use your right hand and use this right hand thumb rule in this manner, such that have the thumb sticking in the direction of the current and grab the conductor with your right hand, then you will see that these magnetic lines of force are in the counterclockwise direction. So I can just quickly draw that as well. Just draw a straight line. and just draw an arrow here, right? This arrow. So this arrow indicates the direction in which the magnetic lines of force are flowing. So now that we have determined the direction of the magnetic lines of force produced by this current carrying conductor, the question then arises, what if we bring these two together, right? What if we bring these two magnetic fields together? Now here we need to make an assumption. We need to say that this magnetic field, that is consisting of these parallel lines, will be in the same plane as this magnetic field consisting of concentric circles. So if we say that this current carrying conductor were vertical and therefore these magnetic lines of force are in the horizontal plane, then let us assume that these magnetic lines of force, which consists of parallel lines, are also in the horizontal plane. It's important to say that we are all having the same, we are on the same plane of reference, right? Otherwise it gets a bit complicated. So if that were to be the case, actually maybe I should just move all this a little. And let me select it and move it up. And select this. And move it up as well, so that I have some more space and we can draw this here. So what we are trying to do is we are trying to merge these two. What we are saying is that this current carrying conductor is in this magnetic field. We can push this current carrying conductor between this north pole and south pole. So let me just copy this north pole and south pole and bring it all the way down here. And let me just delete all these magnetic lines of force. We don't need them for now. Let me capture this current carrying conductor, bring it down. And let me also get this arrow, because the current is still in the same direction. Turns out only one half of the arrow made it back, so I'll just draw the other one. So current is in the same direction. So therefore this magnetic field produced by this current carrying conductor will be the same. And since we have the same north pole and south pole, it will still produce the same magnetic field, or at least will try to produce. The question then arises, if both of these are trying to produce a magnetic field and these two magnetic fields are in the same plane, alright, so they are in the same plane. If that happens, what's going to happen to this interaction between the magnetic fields? Okay, this is what we're going to do. So now that we have brought this in, we are now going to bring these two magnetic fields together. So to do that, I'm going to delete all this. The idea was to just tell you what we're trying to do. Now we can just deal in the same plane. That is one single plane. We're dealing with these two magnetic lines of force. So the first question to be asked is, what happens when you have these two magnetic folds interacting with each other? Now there's one rule with magnetic fields: they do not intersect. Magnetic lines of force do not intersect each other. So for example, if we have one magnetic line of force coming in this direction and another line of force coming in this direction, they will not intersect each other. These two will not cross each other. The question then, what happens? What happens is very similar to what happens when we are driving those cars in amusement parks, those dashing cars. It's similar to a dashing car. So for example, if we have such a case, you will see that this magnetic field will bend away, and this magnetic field which is coming in this direction will also bend away. So it's just the way these two, it's similar to a collision of vehicles. When two vehicles collide, the question is, both vehicles kind of get deviated from their course. Now of course, it also depends upon which is the stronger one. So for example, if a small car crashes into a big truck, not much will happen to the truck. The car, however, will get crushed. On the other hand, if a truck crashes into a car, then the car is going to be crushed and the truck again will not be affected. So if one magnetic field is very strong, it could completely overcome the other. So for example, if let's say the horizontal magnetic field were very strong, there may be only a minimal deviation, while the vertical one may find itself badly deviated, right? Because this is how it is in any collision. Always the stronger field overcomes the weaker one. So let's go back here. Let us assume for the simple case that both fields are equally strong, or even if they are not equally strong, they are comparably strong. So we are not talking about one completely overcoming the other, they are both equally strong. So if we do have such a case, what this means is that if we bring these two magnetic fields together, neither of them will be exactly how they are if they were as they were independently. Independently, we had parallel lines of force produced by these two magnetic poles, and here we have concentric circles as magnetic lines of force in a particular direction. Now if we bring these together, this entire structure will change. So for example, we cannot say that these will be completely parallel lines of force, nor will these remain concentric lines of force. So this interaction will result in such a collision, and therefore both these magnetic fields will experience change. The question is, what change? And that's what we're going to look at now. So let us say we start drawing one particular line of force, right? Let me pick out the biggest one. So let me copy this and bring it here. And let me start with some parallel lines of force. So for example, let me just draw some freehand diagrams. Let me say that there is one parallel line of force here at the extreme going in this direction from right to left, or sorry, left to right. And there is one here at the bottom which is going from also left to right. So the same parallel lines of force, right? Now, in such a case, what happens? As is quite obvious, actually, let me delete this. It is confusing to have an ellipse now, so let me just delete this ellipse and draw a circle, because we are dealing with this entire interaction in one horizontal plane. So it's actually better to have a circle rather than to have an ellipse, right? So now again, let me draw straight lines, because it's so one here and one here. Let me just copy this actually. And there'll be several more, but let's start with the extremes. So if we now examine the interaction between these two sets of magnetic lines of force, that is one in this horizontal direction from the left to right, and the other in the other is this circular line of force which is in the counterclockwise direction, then in that case we can use the same analogy of the collision as we did before. So for example, if we assume these two are colliding into each other, right? In that case, at this part of collision, at this interaction point, you will see quite obviously that because of this line of force and this line of force, here this magnetic field will become elongated. And at this part, this magnetic line, this circular magnetic line of force will become a little squeezed at the top. So for example, let me just draw it. This line of force quite obviously will move upwards. It cannot move downwards, because if it moves downwards, it will intersect with this magnetic line of force, which is not allowed. Similarly, this magnetic line of force will also move downwards, because it cannot move upwards, right? Because of this collision, it has to move downwards. Now, let me delete this circular line of force and draw in freehand what it will look like. As already said, because of this collision, here there will be an elongation. and it continues to be almost an ellipse, and here there is a contraction, right? So what was first a circle has now become elongated at the top and has become squeezed at the bottom. The reason is because of this interaction between them, right? So you can therefore see that because of this interaction, both these magnetic fields have altered, right? This horizontal magnetic field is altered, as well as this concentric line of force has also altered. And the result is we now have a very different shape to the magnetic field surrounding the conductor. So the conductor is somewhere here. This is the top view. So this conductor is somewhere here. But the magnetic field that is immediately around the conductor has now completely changed. So I'll just delete this. And let me just complete the remaining lines of force. So for example, if I say that there were other lines of force, they would all be in this direction. Just assuming that there is no intersection. And of course, they would complete around, because always it has to start at the North Pole and end at the South Pole. And the same here as well. So as you can see that we now have a very different magnetic field, and here too we can complete this in the same direction. Right? Always it's a little, you could say, egg shaped, right? That is squeezed at the bottom and a little elongated at the top. Again, a pretty bad diagram, but I would say think about this logically from the perspective of imagining this interaction between magnetic fields similar to a collision between vehicles, right? That is, vehicles of the same size, and in that case you will see that this is what happens, right? And you can even try to reverse. If you reverse the current, you will see that this magnetic field changes because it will now become in the clockwise direction. And if it is in the clockwise direction, you will see exactly the reverse happening. That is, this elongation will happen at the bottom and this squeezing will happen at the top, right? So with this, I'm going to end this lecture as it's gotten pretty long. But the main idea behind this lecture was to describe how the magnetic field surrounding the conductor changes because of the interaction between two magnetic fields. And this interaction between two magnetic fields is what also happens in an electric motor. So in the next lecture, I'm going to talk about how, because of this change in the magnetic field, there will now be a force. And this force is very similar to the force we saw when we brought two magnets together. That is, either they attract or they repel. If we bring two opposite poles together, they will attract. If we bring two similar poles together, they will repel. This is something we already know. But here it is not so obvious, and therefore we can use this magnetic field pattern to determine the force which is exerted on this conductor. There will be a force. And there is not only can we determine it using this magnetic field, there is also a very convenient law that we can use to determine the force that is exerted on a conductor when the conductor is in a magnetic field. Of course, the conductor has to carry a current. So, with this, I'm going to end this lecture. In the next lecture, we will continue and find out what is the force which is exerted on it, and I will introduce Fleming's left-hand rule, which is the rule for determining the direction in which the force is exerted on a current-carrying conductor. So, if you have any doubts, please do either comment or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week. Thank you so much for listening, and goodbye for now.